Yeah. Uh, so this booklet will be this video will be talking about part 3 for module 5 advanced mechanics. Talking about motion in gravitational fields. This is part 1 of this topic. Okay. Right. So multiple choices. First question: a gravitational force magnitude of F is presented between two masses. What would be the new magnitude of the force if the distance of two masses was halved? Okay, so we know that the gravitational force was actually proportional to 1 over r squared. If distance between them was halved, you actually get 4 times of the initial F with the square here. Okay, so D is the answer. Question 2, there are numerous reasons which contribute to the variations in the value of the acceleration due to gravity on the surface of Earth. Which of the following will not be a reason? So the correct answer is C, because position of Earth in its orbit around the sun has nothing to do with like the gravitational acceleration that we experience on the surface of Earth. Okay. Yeah, shape of Earth does affect, because like if you go onto a mountain, you actually are far further away from the center of Earth, so you feel less gravity, a very slightly less gravity. B, variation of the thickness. Yeah, because like you take a part of the Earth, it actually has more like mass distribution there, so you will feel a heavier gravitational contribution. D, yeah, height above sea level. That's obviously because that's the R term in the gravitational force equation. A faraway planet, Xerox, okay, Xerox, has a mass of that kilogram and average radius of this much meters. Acceleration due to gravity on the surface of that will be equals to. So this question pretty much is substitution of values into a gravitational field strength equation, which is equals to which is equals to G times the mass of this planet divided by R squared. Yeah, and then you will end up getting 5 meters per second squared. Question 4, which of the following statement best describes how a satellite can maintain its stable orbit around Earth? Um, okay. Yeah, so the gravitational field provides the necessary force to apply the centripetal force. Okay, right. So D is the right answer. A says that the easterly rotation of Earth helps the satellite to maintain its momentum. That has nothing to do with the satellite's momentum. Earth is rotating by itself. B, satellites rocket thrusters are constantly ignored. That's not necessarily true. Like we discussed in circular motion does not need any external work to sustain. Okay, so satellite doesn't need to use its thruster to sustain circular orbit. Okay, the centripetal force, as long as the gravity is applying it, everything fine. C is wrong because it says that Earth orbits around the sun provides enough momentum. Again, that has nothing to do with the satellite's momentum. Okay. Question 5, the orbital speed of the satellite around Earth is this. What is the orbital radius of the satellite? So we have derived something called the orbital velocity during lecture. Okay, so it was v equals to square root of gm over r. Make sure you derive this all the time. Okay, and then you can rearrange for your radius. Okay. Question 6. Two planets, X and Y, orbit the same star in a distant galaxy. When X completes one revolution, Y completes exactly 8 times. Okay, so this question uses the very nice result that we discussed during the lecture. Okay, if you know it, this is actually Kepler's third law. If you don't know it, this was like the r cubed to t square equation. If you're not familiar with it, it's actually okay because this will be extensively revised on the next part of this topic. But like for now, if you can go to page 7 of the lecture, okay, it actually tells you like this is equals to this divided by 4 pi square. But because of this term is like a constant, so what that means like you can relate this to like different planets orbiting the same star. So you can say that this is x radius and x period, and then you can relate this to y, and then they'll actually be equal in this equation. Okay, if you just manipulate the equation and then substitute all your like relationships, you actually get the ratios. Okay, right. So have a look at this question if you don't know how to do it, and then ask question if you want. Question 7: a dwarf planet orbits the sun with a period of 40,000 years, average distance the sun to Earth, 1 astronomical unit. Again, that's another direct application of the r cubed to t square equation. But this question gives you like bunch of like stuff that you like astronomical unit. What the hell is that, right? So like 1 AU is just it's just a distance. It's just like a unit for distance. It represents 1 AU represents distance from the sun to the Earth. Okay, the very interesting part effect of this equation, so the Kepler's third law, is that if you use this equation to relate different planets, and if you rearrange this equation, you actually get a very nice sort of ratio between the periods and the radiuses. Do you see how unit doesn't really matter? Because like this equation is equivalent in this way, and then this way you can actually get rid of the unit, just cancel. So as long as you keep track of all the units, you don't change your unit during your calculation, or everything should be fine. Like you should end up with the same unit. Okay. So this equation actually accepts the different types of unit, and you don't have to convert it. Okay. Very nice. Question 8. It says that a satellite is in a stable circular orbit around Earth. So the Earth's orbit is in general not a perfect circle. Okay, which of the following statement best describes the satellite's orbit and Earth's orbit around the sun? Okay, so C is the correct answer because it says that Earth's orbital speed around the sun changes throughout its orbit, um, whereas satellite's orbital speed remain constant. Okay, because it says that a satellite is in a uniform circular motion. Because a stable circular orbit is a uniform circular motion, but it tells you that Earth is in general not a perfect circle. I put a footnote here. It is still an ellipse. We're going to talk about this in part 2. Okay, but yeah, C is the right answer. Question 9. Two satellites X and Y of equal mass orbits the Earth at different altitude. Satellite X has a greater altitude than Y. Which of the following statement is correct about that? Okay. Because they have equal mass, okay, and then satellite X is greater altitude than Y. Satellite Y experiences greater orbital decay. Um, okay. Yeah, so okay, this one is a bit like because it's not technically talked about in the lecture. So let's have a look at all the choices. Part A says that satellite X has a greater orbital speed than Y. Well, that's not correct because if you remember, the orbital speed is actually gm over r. So like Y has a smaller radius, right? So means Y's velocity will actually be larger. Okay, so yeah, then X has a smaller velocity, the A's contradiction. B says the gravitational force exerted by Earth on both sides are equal. That's wrong because as the mass of the satellites are the same, the radius are different, and then Y is closer, so Y has a larger force. Okay, and then part D, satellite X has a shorter orbital period than Y. That's not correct as well because if you recall the important equation here, a larger radius would correspond to a larger period because that equals to a constant. Okay, remember that? So yeah, D is wrong. So the right answer will be C. Orbital decay, this thing refers to like the phenomena where like the satellite is still a little bit in the Earth's atmosphere, so they experience the atmospheric drag to reduce its speed. So it will be C because Y is closer to the surface, right? And it will be larger drag because of that. Question 10. A satellite is orbiting Earth and average magnitude of acceleration is this. You can calculate the orbital speed. You can calculate the orbital period as well. Okay, so from the gravity, right? From gravity, you can use G is equals to Gm over r squared. You can get the radius of the orbital. Okay, mass of Earth is given on the formula sheet, and it's 6 times 10 to the power of 24. Okay, so you can get the radius. After you get the radius, you can use r cubed over t squared to find the equals to Gm over 4 pi squared to find orbital period. And you can use v equals to the square root of Gm over r to find orbital speed. Okay. So the right answer will be A if you check for yourself. Right, question 11. Question 11 says that this question, concept of gravitational force. A, compare the forces of gravity exerted on the moon with a force of gravity exerted on the Earth by the moon. Okay, so Newton's gravitational force of attraction obeys Newton's third law. Okay, so they will be the same, right? Because like one attracts the other attracts this, and they will have the same force but different direction. Okay, yeah. So part B says during experiment of investigation, the force of gravity and between two masses was determined and various distance r. The data shown the linear relationship between the force versus like 1/r². Yeah, it will be linear. Your answer, okay, so explain how the gravitational data supports Newton's law. Okay, because Newton's law indicates like gmm over r squared is our gravitational field of force, and it is indeed our force of gravity is proportional to 1/r², so we get a linear relationship. Okay, right, pretty much just demonstrate that. Okay, it's pretty easy. Okay, please copy this down if you're like if I have marked your thing and then a little bit of wording. Okay, it could be issue on the wording. Just or you can just have a read and see what do you have and I don't have, what I have that you don't have. Okay, trying to get a better response next time. Question C, calculate the force of gravity exerted by Earth on 2,000 kilogram satellite, which is orbiting at an altitude of this much above the Earth's surface. Uh, okay, which is substitution of values in the Newton's law. Okay, very easy. Right. Question 12 says a satellite is in a stable circular orbit around Earth. So the satellite maintains a constant orbital radius r and it travels at a uniform speed v. The mass of the satellite and Earth are mass and capital mass, okay, respectively. Show that this is that. So orbital velocity, pretty much this will be the same thing as we did in the lecture. You can copy the same derivation. But try to derive it yourself because like think about what is supplying the centripetal force. Yeah, gravity is supplying the centripetal force, so it's equal to the centripetal force. And then you rearrange for the v, you'll get the answer. Quite easy. Question 2, a satellite is replaced with a different satellite with twice of its mass. What will happen to the orbital speed? Nothing will happen to the orbital speed because our orbital speed is only dependent to the mass of the thing that is orbiting to. Okay, it does not matter like the small m. It's independent of the small m. So no matter what you put there, it will orbit the capital mass with the same speed. Okay, no matter what. So this is how equation can tell you something that's counterintuitive. Okay, question 12c. Okay, so Kepler's third law. Motion states that the radius cubed to period squared is a constant. Okay, so that relationship. Identify the factors, okay, so determine value of k. So, well, this is pretty much just derivation for the Kepler's law that we did for the class, okay, and then we sort of showed that k is like this thing, right? Right, so then you basically calculate that, okay, and get the answer. Okay, so it's just basically trying to derive this equation from your like centripetal force and the definition of velocity for a uniform circular orbit. And you get this, okay? So yeah. Next question is a projectile on a different planet, I think. Yeah. Yeah, it's a projectile on different planets on Mars. And using the projectile motion, like the data to calculate the gravity, okay? So this is bit revision, right? It's just like the gravity G is no longer 9.8. You have to calculate it. It's quite simple because they tell you how like far it like drops down. So it's like 25 meters. So your vertical displacement is negative 25 meters, okay, which is negative h, times u t sine theta and minus half g of Mars times t squared. They also tell you the time as well, so you can use this equation straight away to rearrange for your GM. Is there anything confusing on this question? Please let me know, otherwise it should be fine. Question B, Mars has an average radius of this much. Using part A, calculate the mass of Mars. Okay, so we know the surface gravity is this much, and the surface gravity can be calculated using Newton's law. I rearrange for the mass to get the answer, okay? So mass is a mass of this much. It's pretty heavy. Okay. Question 14. Question 14 says that a satellite is in a geostationary orbit. Okay. So a geostationary orbit, like I said, I tell you what does it mean. So it means that its orbital period is precisely 24 hours. So as a result, a geostationary satellite would appear to be stationary above the surface of Earth. Okay. So what is the average altitude for geostationary satellite to above the surface of Earth for this period to be possible? So you could use the Kepler's law, okay, and then rearrange for the radius basically, okay? Because period is 24 hours. Make sure to convert that into seconds to get the period, to get the radius in terms of meters. But it's asking for the average altitude, so be careful, right? Because from this equation, this r actually represents the orbital radius, so that extends directly towards your like center of Earth. Okay, so what you want is actually the height above the surface of Earth. That's the altitude. Make sure you get the answer and you subtract Earth's radius from it. Okay. Okay. So question B. It says that low Earth orbit has a much lower altitude compared to geostationary orbit. How would the velocity of the satellites in low Earth orbit differ to the geostationary orbit? Okay, you could say how from the orbital speed, a smaller radius at a low Earth orbit would corresponding to a larger orbital speed. Yeah, it's pretty much just a direct application of the equation. Okay, all right. So question 15. Question 15 was actually HSC question. Okay. Okay. Sorry, give me a sec. Let me just get this started. Okay. So it tells you a bunch of statistics between like mass of the sun, mass of the moon, mass of the earth is on the formula sheet, I guess. Okay. So use this information to calculate the total gravitational force on Earth. Well, so this is kind of like the I don't know, like in module 4, there's a question that asks you to calculate the total like force on the charged particle, and there's like a bunch of other charges nearby, right? It's from sum of force, right? So like on the Earth, there is a gravitational pull from the moon, there's a gravitational pull from the sun, okay? And then you just sum all the forces together, okay? We know that the sun exerts a larger force on our Earth, of course. So just take subtraction and keep track of all your variables, substitute values at the end. You should be getting the right answer. Okay. This question, like if you got it wrong, most likely it's not because of you don't understand the physics. It's likely that you make some very like silly mistake. Didn't square the radius, like I don't know, maybe uh, calculate stuff wrong. Okay, it's basically learn how to use your calculators. Okay. Right. Okay. Right. So question 16. Question 16 was actually very difficult. Okay. This one should be like equivalent to challenging question. Okay, instead of a normal question like I've shown here. So okay, that's kind of weird. Okay, so this question says that the weight, okay, that you experience depends on the location on the Earth's surface. When a person is not on either pole, its weight is affected by Earth's rotation. So if you think about Earth is rotating, and if you're like at the equator, like the Earth's rotation is sort of like throwing you away a little bit. Does that make sense? So it actually means that you're actually undergoing uniform circular motion, like, along with Earth's rotation. Okay, along with Earth's rotation. So yeah, and then you just need to sort of find out the normal force at that point. Okay, because we went through something called the apparent weight back in circular motion. It's basically that. Okay, so question A, given that the Earth's radius is this, okay, at the equator, calculate the tangential speed at the equator. So that's easy. We know that the Earth rotates once every day. Okay, so the period will be 24 hours times 60 seconds squared, or 60 minutes times 60 seconds, so we 24 times 60 square seconds. Okay, and then the radius of the circumference that we travel for every time Earth rotates by once is 2 pi times the radius of the Earth. Okay, and you end up getting 463 0.82 meters per second, and tangential motion. Question B is to calculate the centripetal acceleration at the equator. Okay. Well, you get the velocity and then divide by the square of the velocity divided by the radius. Okay, well, it's quite simple. Radius is given on the formula sheet, of course. Okay. Question C, calculate the apparent weight. Okay, apparent weight is normal force. I can also give you a hint here. For 80 kilogram person at the equator. Okay, so how does this value compare to the true weight of a person? So draw a little diagram here. So like this person on the equator, okay, Earth is rotating, and yeah, you have your weight force this way, okay, and then on the surface of Earth, it exert a normal force to you. Okay, so these two forces actually supplies the centripetal force that you're rotating with. Okay, so you get that equation. Okay, so now if you rearrange it for your normal as Earth is rotating, you actually get normal as this. Okay, the true weight is calculated by your mass times acceleration. You get that. So you get a slightly heavier normal force if the Earth was not rotating. Like if the Earth is rotating, you feel a less normal force because like part of like the normal force goes towards your like, providing the centripetal force. Okay. All right. So question D says that calculate the apparent weights for the same person standing in Sydney. Okay. Sydney has a latitude of 33.865. Okay, that means this angle is 33.865. Okay, so now this person is like a little bit below the equator, so it's undergoing a uniform circular motion in this way. So like this is the radius of the circle. But since it's not directly at the equator, the normal force has to be perpendicular to the surface, so it should be some directions like this. Whereas the centripetal force must be supplied towards the center of Earth like this. And there's a component, okay, of force. So that indicates that there must be like a little friction acting on you, okay, so that you don't slide off. Does that make sense? So it's like normal is this way, right? Weight is this way, okay? And then we have to supply a net force in this direction, okay? Does that make sense? You must have like a friction component in this way, okay? So otherwise you would slide off, okay? So you have to just know that you need a friction in this case, okay, to do this question, okay? It's quite hard. So the person undergoes a smaller circle, okay? So the circle right here with a smaller radius, and this radius can be evaluated from the radius of the Earth, right? From this triangle, this trigonometry. So we know that F is equals to mv squared over r is equals to m times omega squared over times by r. It will be easier to work with angular speed here. Angular speed is 2 pi over t, and eventually get that equation for the centripetal force. So this force is supplied by the horizontal component of the weight. Okay, so like it will be weight force this way, right? But it will be this component, right? So and then now this r is equal to r times sine of theta from the geometry. Okay, so the net force on the x direction is this force right here. Okay, because that's this r here I converted into the big R. Big R means the radius of Earth, and it is equals to the weight force in this components, right? Minus n in this components, right? And then add another force of friction. Okay. And then net force on y is therefore to be 0. Okay, it's therefore 0. We want it to be 0 because like otherwise this person will be like drifting up and down. This is also the reason why we need the friction. Okay. And we end up getting this relationship. So mg cosine minus n cosine and minus some friction times sine of theta. And the difficult part is really to get this friction. Okay. And then if you get from equation 2, you rearrange it for your friction, and then you substitute this into equation 1. And you get that equation, okay, plus that equation. And then you take out the common factor of mg minus n, you will get that equation. Okay. And then so what I did next is I take out another factor of sine theta from this bracket, yeah, and which we can cancel out this sine theta outside, right? So inside I got 1 plus cosine square over sine square theta, which is called cotangent square of theta, and that is cosec square of theta. Okay, because of the trig identity, and yeah, cosec is like 1 over sine square, so you eventually get that relationship, and there you go, and then you can solve for the normal force from that. Okay, if you substitute value, you get this value. Okay, so this value is slightly heavier than the equator. See how it's slightly heavier than when we're at the equator, because we're like doing a smaller circle as well. Uh, yeah, but it's like still less than the true weight force. Okay, the true weight force was like this. Okay, so if you're on Earth, if you're not at the poles, you will actually get like a smaller apparent weight, a very small amount of change, but like still like 3 newtons off. Okay. Um, okay, just give me a sec, give me a sec. Let me get this done. Mm. Okay. Okay. Challenging question, question 17. This one goes a little bit deeper into the gravitational field in its structure. Okay. So derive Newton's universal law. Okay, this is basically direct copy from our lecture, extension material lecture. So pretty much it's just like this law tells you that the total flux of your gravitational field at this barrier, okay, for the two-dimensional universe, right? So it's not a direct copy. This is two-dimensional. Uh, so two-dimensional means like we only have like x and y, so it's two-dimensional. So we have mass here, and then it's surrounded by sort of this imaginary curve called gamma. And then we're saying that it's a gravitational field. And then the equivalent Gauss's law for gravitational field is given as this equation, and we can derive the sort of gravitational field in this two-dimensional universe, right? So, yeah, and then if you just do that, right, and then because we have there's something called the circular symmetry, right? Because like if you on the circle everywhere the gravity should be the same. So like G is the constant around the circle. So you just integrate it through the whole circumference to get that equation and rearrange to get this. Okay. So in a two-dimensional gravity, it's actually proportional to R, inverse of R. It's not proportional to the R squared like we have for three-dimensional. So actually, this inverse square law was a direct consequence of the dimension of our universe. Okay. Question B: compare between the gravity from 2D and 3D universe. How do they change with the distance? Okay, so similarly in both 2D and 3D universe, the field strength is now proportional to the mass, but it will be inversely proportional to different powers of R. So in two-dimensional case, we see that R is inversely proportional. And the force is inversely proportional to the -2 power of R. But in two-dimensional, we have shown that it's inversely proportional to the radius. Okay. Um, but then, so there's a difference of like R, okay, R to the power of 1 here. Okay, so like by induction, you should probably like guess that in 4 dimensions it's probably inversely proportional to R to the power of 3, right? The cube of R, right, in 4-dimensional space. You can also try that yourself. Okay. Question 18. Question 18 is a quite interesting analysis. So you've got a planet that's been like dug through, like in the middle, right? So what's happening if like this person drops like a mass, and then because of gravity, it's gonna fall, and then it's gonna sort of like fall towards the center of Earth. But as it keeps its momentum, but keeps falling, and now the gravity sort of acts upward to try to drag the ball back. Now, because of energy conservation, it's gonna like stop at here and then start to like going back, and then eventually forms like this oscillatory motion, like going down and up like that, and just oscillates. Okay. So this is actually called the simple harmonic motion, like this type of motion. Like it's kind of similar to like object on a spring or something. It will travel like the same thing as this. But in this case, it will be like gravity supplying it. Okay. Um, okay, so derive an expression for the gravitational force Fg, okay, on the metal ball as a function of its distance from its radius center r. Okay. So assume that Earth's density is uniform. So if we assume that the density is m times v, m divided by v, and then it's equals to m of all the enclosed mass. So like if the ball is like right here, and then inside this dashed line is all the enclosed mass, and then the volume is enclosed volume. Okay. And then recall that volume of the sphere is like 4/3 pi r cubed. So you can get the enclosed mass as a function of this radius. Like the radius is the position of my ball, right? As that. And you pretty much just substitute this into that. Okay. So does that make sense? Right. So using the result of Gauss's law on gravity, okay, only the enclosed mass will give you the gravitational field contribution. Everything else above you will cancel out. Okay. Um, Yeah, so like that, and then substitute this value in, you actually get this equation. So the force of gravity is actually proportional to like your location, okay, here. And R, capital R is the constant, okay? Right, that's inside the uh that's inside this planet, okay? And then we know that if you have learned the simple harmonic motion equation, so your acceleration is proportional to your displacement. Right? This exactly satisfies this equation, okay? So it actually forms a simple harmonic motion. Okay. Yeah, we can just times by everything by a factor of m, and then we can derive for the acceleration as well. Okay. Show that the acceleration of the ball is in the form of this, okay, and then trying to figure out what omega is. Okay. So omega is literally this thing, we can just times by the mass. Okay. Um, yeah, and then the question C to say that acceleration is the second derivative of your displacement. Okay. And if your displacement was like modeled as this equation, because like the particle is going up and down. It's sort of like it's a cosine function, right? The amplitude is going like this, up and down, up and down, up and down over time. Okay. You want to show that R as a function P is a solution to this. Okay, so what we can do is basically we can substitute this into the differential equation, differentiate it twice, and we'll see how we get the same result as the left hand side and the right hand side. And when I'm showing how this is our like solution for the radius, for the like position of this metal ball. Right, and then question D is to derive an expression for the ball's oscillatory period T. So does this period depend on where the ball was dropped? Okay. So the oscillating frequency is given as this, right? So it is actually independent to your radius r here. Okay. So it does not depend on where you drop it. The ball would oscillate in the same period, no matter like if you drop it here or if you start it here at initial zero speed, it's gonna oscillate in the same frequency. So it's quite like nice. It's quite counterintuitive. Okay. Meaning that no matter where you drop the ball inside the Earth, the ball will keep oscillating in the same frequency about the center of it. Okay. So yeah, that is it for this week's homework. It's quite long, and especially questions at the end are getting really crazy, but it's quite interesting. Okay, so this is it for this week. Okay, enjoy physics. I'll see you next time.